Good afternoon, sir. My name is Tristan Galvinder, and this is my Part 3 submission for the TechMove GLMS project. Now, in Part 2, we built a working MVC application with a database. The task for Part 3, however, was to modernize that system by decoupling it into a service-oriented architecture. We then containerized it using Docker and implemented automated integration tests. Right now, I'm going to walk you through what was built and how it all works together before we even think about getting into a demo. As you can see on my left, this is the Explorer, and inside is the full solution. We have 3 projects inside the solution. We see the API, which is the brain of the system, and the web, which is the front end that the user sees. In between are the test projects. We also see our Docker Compose file at the root, which orchestrates the entire system. And of course, inside the GitHub folder is our GitHub Actions workflow, which runs the CI pipeline automatically on every single push. I'm not here to waste your time, so let's get into the descriptions and explanations quickly of the codebase itself, starting with the API, which even though is brand new, will seem very familiar to you. Now, this is a brand new ASP.NET Core Web API project, and the reason it's familiar is because everything that was previously embedded in the MVC application has been moved here, starting with the models. Now, these models from clients, contracts, service requests, and of course the enums, they now live on the API because now for part 3, the requirement was that the front end or the web app, the MVC, does not speak to the database. The API speaks to the database. So they live in the API because the API is the only layer that talks to the database. Speaking of the database, here is the data folder with the DB context. And it also lives exclusively in the API. This is Entity Framework Core connected to the SQL server, and as I mentioned before, the MVC project has no database context at all. It has no idea the database even exists. Only the API project communicates with the SQL server. The web communicates with the API, and the API communicates to the database. Now that that's settled, let's talk about the patterns. These are arguably the entire backbone of the system, let alone the API. In part 2, we implemented these 3 design patterns, and now for part 3, all have been successfully moved to the API without breaking. The first up is, of course, the chain of responsibility. Now, this handles authentication. When a service request is created, it passes through the chain of handlers, each one checking a different rule. Now, it checks things like, does the contract exist? Is it active? Has it expired? Is it on hold? And if any check fails the request, it's blocked and an error message is returned. Not an error in the sense of crashing the app, but an error in saying, you cannot submit this, something has went wrong. All of the logic to do with the chain of responsibility now runs perfectly inside the API. Next up, of course, we have strategy, which we use to handle all conversions in the app because, as always, we're working with money across countries. It's TechMove global, you know. Now, when a service request is created with dollars, for example, the API will automatically convert it to South African rands using a live exchange rate. The live API strategy fetches real-time rates from an external currency API. Now, the whole point of strategy is backup plans, backup plans, backup plans. So, if that fails, not because of the app, but let's say the API is down for some reason, it falls back to a cached rate strategy. And if the cached rate fails for some reason, well, then it falls back to a fixed rate strategy as the final safety net. The whole point of the system is to make sure that the system provides a result no matter what. The system will never crash. It will always find a way to do the conversion for you one way or another. Next up, Observer. This handles consistency across the entire system itself because in the make-believe scenario, they used the manual system and it was very inconsistent. Any updates were registered in some places while other places had an older copy, and it was just not good, befitting of the make-believe company of TechMove. Observer negates all of those consistency errors. When a contract status changes, for example, like from active to on hold or terminated, blocked or something, the system will automatically notify all registered observers. One observer will write an audit log, while the other observer finds all pending service requests linked to that contract and will automatically set it to blocked if it's anything other than active. This all happens automatically inside the API the moment a status change is saved. Let's close this, and then we talk about the services. Now, all the business logic lives inside these service classes, from client services, contract services, service request services, currency service, and respectively, each one has its own interface and its implementation of its interface. They are all registered with dependency injection in program CS, and they are injected into the controllers, which I'll talk about next. This is clean separation of concerns, and the controllers just receive the HTTP requests and they delegate to the services. Next up, the controllers. And we have controllers for authentication, for clients, contracts, service requests, and currency, respective to obviously the services itself, Now, every endpoint within these controllers, they return the correct HTTP status code. 201 is the good sign. It's for when something is created. 204 is for another good sign when something is updated. 404 is when something is not found. It's the generational, everyone knows what error 404 means. And 400 is for when validation fails. The contracts controller specifically has the patch endpoint for updating contract status, which is linked to the observer pattern, obviously. The contracts are the most intricate part of the system because, well, they are the backbone of everything to do with service requests, clients, and the system. They are the link between the two. The entire backbone and functionality and main point of the system is all inside the API, but let's briefly just show you inside the web. And the first thing we'll look at is the project file. And as you can see, there are no entity framework packages here whatsoever. There's no SQL server, no migrations, no DB context. The only package is Firebase authentication, and that's obviously for the login system. As I've said 3 times, I think already, the web app, the MVC front end, has 0 database dependency. And in case you don't believe me still, let's look inside app settings JSON. Now in the settings file, there's no connection string. There's just an API base URL pointing to where the API is running. That is the only thing the front end and the MVC needs to know. I know you see the services inside here, but this has been stripped completely. Now the only service is the API itself. All communication with the API goes through the single API service class, and it automatically attaches the JWT token to every request so that the API knows the user is authenticated and is able to access these capabilities. The MVC controllers call methods like getAsync, postAsync. They never touch the database directly. That's really the entire thing I wanted to show you with the web. The tests obviously handle the testing of the system. They have been expanded from part 2 with a full integration test suite, as you can see. These tests spin up the real API in memory using an SQLite test database. We didn't want to use the actual database because every time we run something on a test, it's just going to add it to our actual stuff. So we use an SQLite test database and make actual HTTP calls to the endpoints. We test creating a client and reading it back, creating contracts, changing status, creating service requests with currency conversion, and of course, error handling. These handle every single feature and function and like skeleton of everything we do in the app via the API. This tests the integration between the API and the front end. This might take a few seconds, but let's just show you what's up. And as you can see, all 38 of the tests have succeeded. I think when I run the app, I am going to just pause it so that you can see the final results. So 'cause I feel like that's boring for you to watch. It doesn't help that the VMs are sometimes very slow. I'm sorry. So let's just tidy this up really quick. And we're about that time where the next 10 or so minutes are going to be completely just running you through and showcasing the app to you. So in the same terminal, let me just get a simple Docker Compose app is how we run the system now. And to save you some time, I will come back to you when it's built. Right, it is working. Here's a quick explanation real quick. So Docker Compose brings up the entire ecosystem with one command, like I showed you, Docker Compose up. So first the SQL server started as its own container. Actually, let me scroll up. So first the SQL started as its own container. Then a database initializer container ran our init SQL script to create the database as well as its table. Then the API container finally started and connected to the SQL server. And last but not least, the MVC frontend container started and connected to the API. Now, each container talks to the others using the internal Docker networking by service name. There are no hard-coded IP addresses. The API reaches the database at SQL Server DB, and the front end reaches the API at the backend API. So let me just open Chrome real quick, and let's start off on Swagger. Yep. So to confirm the workingness and the validity of the API that we created, here's the Swagger documentation. Now, as you can see, every endpoint is listed and self-documented. You can see authentication, you can see clients, contracts, currency, and service requests, sorry. Swagger is enabled unconditionally, so it works in both development and production when it comes to Docker modes. This is exactly what the rubric required because it said self-documenting and testable APIs. Showing you inside just real quick for stuff like clients, 200 okay, 200 okay, contracts, next up, the actual app, because this API is just running in the background. This is the real deal. This is Checkmove. The exactness to how it was in part 2 speaks to how new it is, you know? Part 3 has perfectly ported over and integrated everything in its new containers, in its new setup, relying completely on the API. But yet this is perfectly as it was in part 2. This is running from the MVC web app side. The MVC frontend is running in its own container, and as you can see, the login page is loading from the GLMS frontend web container. It is calling the GLMS backend API, which is connected to the SQL Server database container. 3 separate containers, all combined using Docker in one seamless application. It's perfect. So we're just going to stick to it and use the admin account. And let it log in real quick. And here we are. Really quick on the login. Authentication uses Firebase, just like in part 2, to verify the user's identity. After Firebase confirms the login, the MVC app calls the API's authentication endpoint to receive a JWT token. Now that token is stored in the session and attached to every API call. So we have 2 layers of authentication, the Firebase for the user and JWT for access to the API. Real quick, let me just leave the VM. Here is the authentication side of Firebase. These are all the users that I've currently created and have access to the system. I've forgotten about 3 of them's passwords, which is why I'm opting to use for admin, because it was auto-saved on my VM system with the correct password. So here is the main dashboard. The dashboard loads the client, the contract, and the service request counts accurately by calling 3 separate API endpoints. Now, all of this data is coming from the database through the API. The MVC itself has no idea where the data is stored, but it's receiving it. So that's all that matters. I've explained the code to you. I've showed you in Swagger how everything is reading 200 OK, and that, no, I don't want to do that. Everything is, by my word, integrated properly, but now it's time to actually show you. You've seen the code base, you've seen the structure. Does the structure that I've shown you work? Well, let's start off by creating a client. Here we see 2 from last time. Let's add, first let's edit, let's show you edit works. Let's pretend he is the and there you go, perfectly updated. You can view his details and the respective contracts linked to his name and delete. I'm not going to delete. Can, don't want to. Let's create another client. Let's go Kyle. And make his region Portugal. There we go. Kyle. And he'll obviously have nothing linked to his name and the respective Now, creating a client sends a post request to the API, which validates the data and saves it to the database. If it's correct and it's created, it will return a 201. The MVC controller receives that response and will show the success message that you see up top here. This means a 201 has been received, and this has been received, well, in this case 204, but 201 or 204 when something has been successfully completed. Next up, contracts. There are 2 already created from the last time, and as you can see, when I updated Akil's name, his name updated here as well. Just to show you, I can download the PDFs. Here we see contract dummy has downloaded, same from last time. I can edit, specify the car type, and it updates. And of course, okay, we'll wait till we can make a different one now. Okay, so let's select a client, put it towards Kyle. Let's make this one make it today's date, and we'll put this as the due date. That's not the due date, but anyways. Okay, make the contract status on hold, service level premium. We'll attach dummy document 1 to it. Boom. As you can see, creating contracts works exactly the same way. The API validates that the end date is after the start date, because that's logic, and that the client we are applying it to even exists. And if anything is wrong, it returns a 400 bad request with the specific error message. Again, error doesn't mean it crashes the app. It means it will return a red message up here. But obviously, because we were successful, we created the contract for collecting rocks. I specifically made him be on hold so that I can show you the filter of the system still works as well. Here are the 2 that are active, and on hold you should only see Kyle, which there you go. Back to contracts, just to show you that again. And then we do service requests, the final but also very important part of the system. Because the service request, as we know, runs through the chain of responsibility behind the scenes. Checks different aspects about the contract, like if it even exists, is it active, is it expired, on hold. All checks go past the system. It's in this you also see the chain of responsibility in action with the sending through of a service request. We also see the strategy in action when it comes to the service requests. So creating a new service request. Let's just make it first. Oh, let me make Kyle active now so I can do it to him. Kyle's now active, which means I should also now have access to him here, proving that that part of the system works unintentionally. And here we'll enter something in, like my favorite number, and it will update in real time using the API strategy. If I went at $6, it'll be that. If I went at $1, that's the current exchange rate of the world. Let's make it that. And send it through. Boom. Successfully created. So, like I said, here you see the strategy pattern in action as well as the chain of responsibility. As I typed the amounts, the JavaScript called the currency API endpoint, which fetches the live exchange rate and converted it before your very eyes in real time. Now you can see the rand amounts and the exchange rate updating. The system, if it had to fail with the live API, it would have used a cached rate on submission or a fixed rate. It tries a live API first and will fall back to anything if it's needed. And like I said, chain of responsibility will check everything is in order before allowing it to even create. The final thing that I will show you is inside of Docker Desktop itself. Here we can see it all. You can see all 4 containers, right? The database creates the init and then exits, so that's on purpose. But you can see everything running as intended. The SQL server, the API, the backend API, and the front-end web, right? Everything running correctly and doing its job. This is the full containerized ecosystem running on a single machine through the one Docker compose up command. This shows you everything that you just saw is containerized on Docker Desktop, and that it actually has been running in the way I've said it's been running. I truly do feel that's everything to showcase about the system. So to summarize what was delivered in part 3, the MVC monolith from part 2 has been decoupled into a service-oriented architecture. The API now handles all business logic and the 3 design patterns and all the access and communications to the database. The MVC frontend has 0 database dependency and communicates exclusively through HTTP clients and talks to the API, which talks to the database. We use automated integration tests to run the real API endpoints and verify the data's integrity, and the entire system runs in 3 Docker containers orchestrated by Docker Compose with internal networking. We have in GitHub a GitHub Actions CI pipeline, which ensures that every code change and commit to GitHub is tested first and then deployed automatically. Just to showboat, let us go here, and here is our GitHub in its current states. Here we can see the packages for the API and the web, everything together as intended. Most recent commit was our referencing. And yeah, I still need to do the README file, but that's it. Thank you so for watching. I hope this has shown you everything you needed to see about the app itself and how everything works together, and hope you enjoyed. Danke.